All right, why don't we go ahead and get started? My name is Eric Jebsen. For those who don't know me, I'm the current chair of the American Nuclear Society Chicago Section. I'd like to welcome everyone here to our June presentation, this one from Alex Wheeler of Curio Corporation. Before we get started, though, just a housekeeping item. Please put all your questions in the Q&A, and we'll monitor those. And before we get going on the meeting proper, I wanted to share some information with the folks on the screen who may not be as familiar with all the things that the Chicago section has done. We run in a almost an academic year situation, or a fiscal year that runs from July 1st through June 30th. And I had a request from one of our board members that maybe I should highlight some of the things that we've done through the year. So without taking away too much from our speaker, I'm going to go ahead and share my screen and just show some of the things that we're doing or we've done through the year. Let me know, someone, if they can see the slide on the screen.
Yeah. Looks good, Eric.
Okay, thank you. So again, just introductory slide. And, you know, the things that we've done, just a couple of slides here. We are almost complete of our merger with the Michigan, Ohio section. We'll have a new section called Chicago Great Lakes. You know, just Michigan by itself borders 4 of them. So if you have anything to do with Michigan, you've got 4 of the Great Lakes right there. And we expect that to be approved. It was approved by our boards actually last fall. And we've just been tweaking the bylaws and rules and we have a couple of committees that we have to get approval from. And we've gotten those, and then we're just waiting for the final approval at the national conference, which is the week after next. In terms of section meetings, we've had a number of really interesting presentations this year. NuCycle, for those who could attend, presented in November. We had a student showcase of work from 3 universities in February, and that was very interesting. Wide diversity of topics, as you can imagine. A HALEU fuel impact presentation from Dr. Bachman in March. Curio, we're meeting now, and we might have a meet with the president, Ken Peterson, current president of the American Nuclear Society, wanted to just get together in person, and we're working on that. So for those on the meeting, just take note that we'll be sending out a notice at sometime after the annual convention or meeting. We'll meet with Ken, and technically he won't be the president then, but he will have just been. So it's a good opportunity to get his input on things, his experience over the past year. And then finally, we did a lot of outreach things this year. We had Boy Scout Nuclear Science Merit Badge. We participated in that for, I guess it was 8 scouts, and very well received. We had the Cloud Chamber, and they dressed out, and it was really well done, well received. A Washington Award, very prestigious engineering award. We helped support that financially and attended in February. Very interesting there. High Night, which was March 14th, 314. Was a STEM activity. Chicago Public Schools, we were judges for their exhibition. They had a lot of student papers and projects presented, and we judged those and handed out 6 awards. And then the last thing that kind of closed things out, as you can imagine, these run in their own academic year. They kind of wind down in April, and we had a STEM Fest all day at the Romeoville Library, which had approximately 2,000 people attend. And we attended last year, and had a table kind of like in the back of one alcove, and it was, I guess, well received because we were kind of front and center when you walked out of the stairwell. We were right there. So, and again, it was really good day spent. So, with that, I just wanted to pass on what we have been doing. I'll stop sharing here. And with that, I will turn it over to Alan Metzger, one of our members, to do an introduction proper for our speaker. So, Alan, to you.
Okay, thanks, Eric. I want to introduce Alex Wheeler here. Alex is a senior network engineer with Curio, and Curio is kind of focused on closing the fuel cycle. Some of you saw the short introduction we sent out about this meeting, and so you've probably seen that. I saw a presentation from Alex at the Thorium Energy Alliance conference a couple of months ago down in Abilene, Texas. I thought it was pretty compelling, and I thought that it would be similarly compelling to those of you in this section. So with that, Alex, the floor is yours.
All right, thanks for the introduction, and thanks for the opportunity to present here. I'm going to share my screen real quick. Wait a minute. This is it. All right, you guys should be seeing a presentation. Let me know if not.
Yes, it's good.
Okay, great. Okay, I'm Alex Wheeler. I'm a senior nuclear engineer at Curio. I'm here today presenting about what Curio is doing, what we want to do. So without further ado, so Curio is a nuclear startup company. We are primarily focused on closing the back end of the fuel cycle. We are pursuing several other opportunities that closing the back end of the fuel cycle opens up. There's a lot of fun technology, a lot of fun science that can happen there. So we want to pursue all of that. So the problem with nuclear waste. Now, if you talk to the average person, they will say that nuclear waste is a problem. Once you become a bit more educated on the matter, and you talk to other educated people here, like in an ANS, they'll say it's really more of just a perception problem. I'm going to tell you why I think this is also still just a problem. So first off, with fuel, when you put it in a reactor, you're only going to use about 4% of it, depending on the burnup. That leaves like 96, 95% of the stuff that's in that waste is still fuel material. Back in the day, we had we thought we could put it all in Yucca Mountain, right? Issue being that Yucca Mountain did not come to pass. It was in the law that it was supposed to happen forever ago. Obama said we're not doing it, and then Trump confirmed that we're not doing it. So it's pretty bipartisan that Yucca Mountain is just not going to happen. Instead, we just leave the fuel on site, and because the utilities paid into the nuclear waste fund, now they sued the government, saying like, hey, we paid a bunch of money for you guys to take this, to throw it away, and you're not doing anything with it. So instead, the US government pays about $1 billion a year just to store this spent, lightly used nuclear fuel on site. And in some cases, in abandoned sites, places where there isn't a reactor that isn't generating power at all. As a result, we have close to about 90 metric tons, pretty close to that. We add 2,000 metric tons to that every year. It's at 81 different sites all over the place. And really, when it comes down to it, it is also the perception problem is a big problem. We have about 12 states that have bans on nuclear power, and about half of those mentioned that there is no solution to this nuclear waste. So we feel the solution to this is recycling. What our vision is to eventually commercialize a large NuCycle facility. This would be our patented recycling process, and we want this to be a large facility, something that would recycle 4,000 metric tons a year. Right now, that is significantly more than the world's combined recycling power, right? The biggest site is Log, which is 1,600 metric tons a year. This is going to double the world's capacity for recycling. But we need that. We need that because we have this 2,000 every year coming in. And even with that coming in, if no more nuclear is ever built, with just the reactors that are here right now, this facility would run for 50 years, still recycling material. I do hear from some technical people sometimes that, kind of encouraging that recycling is a good idea. You have to recycle. I also want to be clear here. You don't have to recycle. The only thing we had to do was we had to put this in Yucca Mountain, but we didn't end up doing that, right? So you really have to present a strong economic case, a strong value case for why we actually need to recycle. And that's what we are looking at here. And with our recycling technology, what products can we get out? And the uranium that is in this spent nuclear fuel, if you re-enrich that and put that into reactors, that will provide something close to 40% of the nation's fuel needs. We'll also produce quite a lot of this transuranic fuel. That's something I'm going to talk about a bit more later. It's be something kind of, I guess, our take on MOX. But we're not just looking at this fuel. We're looking at several other products, specialized radioisotopes that you only find in nuclear waste. There's other material that is in there that is worth a lot of money. And with this, you can take a strong case to say, yes, the nation should recycle its nuclear waste. And in doing so, we want to take the current waste volume, high-level waste volume, and reduce that by at least 96%. And we want to really take this, what everyone talks about as, 10,000 year plus, million year plus storage burden, and take that down to about 300 years. So the technology that we think would unlock this is what we call NuCycle. This is a patented process. Curio actually has a patent that is published out there if you guys want to look it up. It focuses on, I guess, 3 main unit vessels. And that would be our decladding vessel, our chemical decladding, and we do that via oxidation. Then we have our fluorination vessel. And so you get this decladding at the first unit vessel. We'll turn this into a nice homogeneous powder. We take that to our fluorination vessel. And what we want to do is different from other past fluorination efforts. We want to do this thing called a selective fluorination. Right now, we're looking at NF3, and that is a fluorinating agent that is very weakly fluorinating. It's not as dangerous as, say, fluorine gas or HF, but it has this really neat property to it that at low temperatures, it will not fluorinate things. You have to increase the temperature to get it to react to certain things. So what ends up happening is that the fission products these, what you would actually call the waste material, that would react and fluorinate and volatilize out at lower temperatures. And you can raise the temperature and then get out pretty pure UF6. And that can go straight into the current enrichment front end of the fuel cycle process that we have today, right? It doesn't need any new supply chains for that. It is also, NF3 is also not as strong enough of a fluorinating agent to get these transuranics. So that it will fluorinate them, but it will not volatilize them. So that makes it a great candidate to pair it up with these, current pyroprocessing techniques and do some electrolysis on them. And that's where we get TRUfuel out. So you get pretty pure uranium stream, and then you can get this, metallic advanced reactor fuel that you could put for advanced reactors or even for current light water reactors. So we set up a proposal to study NuCycle. We had a series of tech goals. We wanted to, with our deox, our chemical decladding, significantly take the fuel that is currently reacted and in contact with the cladding and separate that and get these nice homogeneous particles. We also want to look at some off-gas management. Krypton 85, it is something that is very important for regulatory purposes. You can't emit too much of that, but it's also a very important isotope for leak detection. Right now, Krypton 85 is only produced in Russia, and we use this for leak detection for things like our subs, right? And we use it for defense purposes. And in the last couple of years, we just found out that's probably not a good idea to rely on Russia for some of these critical isotopes like that. So we really want to recover a lot of these key isotopes. And fluorination, we want to show that we can take out 99% of the uranium, that bulk material that is waste. And we want to show that it can be pretty pure. Right now we have some, lab scale demonstrations on simulant material. But in that we're meeting ASTM standards for UF6. So that's pretty game changing when it comes to recycling of uranium in the fuel cycle. And then we also want to look at the end with electrowinning. Here we want to look at the co-extraction of these transuranic products. We at no point in time want to extract pure plutonium. This is from a safeguards by design perspective. We don't want pure plutonium whatsoever. We want to make sure we get all of these actinides, because these are a lot of these actinides. These are the things that are the 10,000 year waste burden, right? We want to get rid of that. There's also several precious metals that we want to get out as well. And, we're looking at seeing what sort of reduction potential we need to get those out. And then strontium-90 and cesium-137, those two are some of the most important isotopes when it comes to disposal of nuclear waste. They alone account for something around 80% of the heat generation. But something like strontium-90, that is excellent when paired with RTGs or things like that. There's companies like Xenopower, Nanodiamond Batteries that are looking at utilizing this as a power source. We want to use that. And cesium-137, that could be a gamma source if used correctly, but we really want to get those out because those really constitute a lot of the waste volume as well, or heat generation, I should say. We proposed this to ARPA-E, and to our luck, they decided to fund us. We are looking in the ARPA-E program mainly at the first two unit processes, the deox and the fluorination. The deox will be happening at Oak Ridge National Lab, and the fluorination will happen at Pacific Northwest National Lab. We have Sandia National Labs to do safeguards by design for us. And we're also partnered with Spectratech to look at the what is the handling of the fuel assemblies when you would get them to a facility like this before you'd put them into a NuCycle facility. With all that, at the end of it, we have a fully integrated lab scale demo that we'll be demonstrating at INL. They have a space for us in the hot cell where we can demonstrate this with actual used nuclear fuel. We have about 3 kilograms set aside from Byron Nuclear Power Plant. We're really excited to see what it looks like in actual irradiated fuel. These are the PIs in the project. Vic Singh, he's the inventor of this. He's a chief innovation officer here at Curio, and he's a pretty smart guy. He's looking into this. But we have Lee Martin at Oak Ridge doing decladding, Bruce McNamara doing fluorination at Pacific Northwest, Ben Sapiti at Sandia. We used to have Ken Marsden for INL, but he got conflicted out. But now we have Morgan Kropp. She's very capable, and she's been with us the whole time, so she really knows what she's doing there. And we're partnered with John Scaglione at Spectratech to look at the pre-process, the front end. So what happens if you pull out all this waste material? What are you left with? It might not be exactly fair to compare with Purex, because Purex, I guess, they're really only been implemented as energy independence means. But we are looking at dramatically reducing the waste volume that comes out of it. When they were looking at Purex, they were looking at had a different value set. They're looking at resource utilization, at energy independence. Nowadays, it's different. It's all about the environment now. And I think you really need to show how your processes in the future are really environmentally friendly. And that's something we want to look at here. But when you have such small waste volumes left over, you open up these other opportunities for waste disposal. The reason they went with Yucca Mountain is they had multiple options. They thought that would be the cheapest given the amount of volume that would come out, to just have one singular repository. There are other options that were proposed, and one of them was deep boreholes. These are just very small, incredibly deep holes that go, so far down into the rock that even if something like the container broke, it would take millions of years for these isotopes to transport back up to the biosphere. So once you put it down there, it's not coming back. I mean, originally they thought that you need so many boreholes that you wouldn't have the economics. But if we take out all of these waste products and find a market for them, that's including strontium-90 and cesium-137, we could fit all of the waste that's in the US right now in 4 boreholes. And with that heat generation loss from strontium and cesium, you could have them less than 10 meters apart. So that's tiny. That's like a small office that could really hold all of the nation's waste. Right now, we're partnered with, we have a public-facing MOU with Deep Isolation. They are a company that is looking at a deep borehole methodology, and they're currently working on their universal canister. So we're hoping some of our waste forms can fit into that. So a lot of these products have a pretty straightforward market, like uranium would go directly into the market right now. But what do you do with this, plutonium-based TRUfuel? There has been a MOX program.
Hey, Alex.
Yes.
Hey, let me slow you down because I think we're getting into the next little section here. So there were a couple of questions
Sure.
that I saw, just to slow you down. Now, one of these, I think you touched on comparing the Purex process, because that was a question I had myself, was, you know, if you're doing this, are you going to end up with a huge amount of waste, liquid waste, that's going to be in tanks? They leak, you know, how sort of those legacy problems from the earlier reprocessing we've done. And so one question I had, and you touched on it versus the Purex, was the so the waste product that comes out that's true waste that you would bury in the deep borehole, is it a pellet, a solid, a liquid? Do you know enough yet to know what that form is, or all of them?
Yeah, so, and maybe I go back a little bit more. In our 3 unit processes, our deoxyfluorination, electrowinning, we'll have waste forms that come out of each one. Right now, we're talking with some people at Pacific Northwest about doing a study for what is the optimal waste form for each one of these. So I can't give you a definitive answer on what they look like, but the big problem with Purex is you're really just chopping up that fuel. You're dunking it in nitric acid to begin with to dissolve it all. And that's where you start to get these large volumes of waste.
Right.
Our process is meant to be dry. We're just putting it in the first unit vessel. We're exposing it to oxygen, converting that UO2 to U3O8 powder that is separated from the cladding. And then with fluorination, we're just, whatever will volatilize with the fluorine will turn into a gas that we can capture. And then we would convert, or I mean, it's at high temperature, right? So it might not be a gas at lower temperatures. And then the last step, they will be a salt form. So we'll be doing a study. I'm not exactly sure when, probably starting at the end of this year, next year, on what the exact form will be. But yeah, hopefully that answers your question.
Yeah, so I think that the root of the question was sort of a large volume of basically contaminated sulfuric acid waste versus what seemed to be, you know, there was the gas that might be used for, you know, further enriching, but you know, at least a dry powder form, which seemed like way easier to handle, and you don't have these the problems associated with a liquid.
Yeah, yeah, it's these big vats that you put them in initially, like you dissolve it, and that is your problem. And a lot of this also volume reduction comes down mainly because most of it's uranium, but also cesium and strontium. Those tend to be your limiting factors. You can only, if you put it into a waste form, you can only put so much in there, right? To meet heat limits for that.
Okay.
So
Go ahead.
okay. Great. Okay. So we're looking for possible markets to put TRUfuel. This is plutonium, primarily plutonium and uranium based fuel material. So one of the people we are partnered with is Lightbridge. If anyone's familiar with their fuel, they kind of have this Twizzler looking fuel that you see here at the top left. That shape is actually spun around, and you don't need spacers with that. That is a metal fuel they want to put in light water reactors, and they, according to the results, they can increase the safety parameters of the reactor itself, so they can have these nice power uprates with it. They also really want to get to higher levels of burnup with this. Right now, what you're seeing is some stuff that I pulled out of an open sourced publication on their fuel for neutronics. They had it in the publication for 15% HALEU. I think Lightbridge himself wants to go up to even higher enrichment levels of HALEU, or even lower at the beginning, but depending on the application. But we have some of our comparisons for TRUfuel with that, and you can see in black on the right here. That is HALEU that you would have in this system. And then the other colors are different forms of TRUfuel, depending on how you want to extract it. One of the things with the volume of material that we'll be getting through, we have some room to play with what the actual material concentration of TRUfuel will be, right? Depending on how long your fuel has been sitting there, it will have more americium than plutonium, and more americium because some of the plutonium will decay into it. Higher burnup material fuel will have more of these transuranics that are built up in it. So we can really homogenize this with this large volume. So we have a question of, what form do we want TRUfuel to look like? And for something like Lightbridge, something like TRUfuel without the minor actinides, that looks pretty good. That can get to very high levels of burnup. So you could have this fuel in there for quite a long time. And of course, when you're comparing metal transuranic bearing fuel, you have to really look at the EBR2. A lot of these fast reactor companies, they'll say, I've seen a lot of them say that they're basically just the EBR2, or they use all the same principles as EBR2. So that's a really good open source reactor that you can compare how your fuel would act in it. So on the right side, you can see the neutronics of that. So this is the multiplication factor. In black EBR2, they actually had 66% enriched HEU. You can't get that anymore. So in the dotted line, that's what HALEU would look like in this. And you can see TRUfuel, it does great in the fast spectrum. You get these really high neutronics, these really great neutronics in the fast spectrum. And the thing is, you also get more neutrons per fission, especially in this fast spectrum, when you want a lot of these companies who want to have these breed and burn fuel cycles, this is something ideal for them. So those are just a couple of results. We also looked at a couple of other reactors, like a TRISO-fueled reactor and a molten salt reactor. The primary idea with those studies, and it's something we will probably publish sometime in the future here, is can TRUfuel fit into reactors that people are proposing? But the real value would be in having a reactor that is ideal for this fuel that you're going to produce. So that is something else we want to look at. What type of reactor would look best with this? That's something our CEO, Ed McGinnis, he'll always say, like, he'll bring up the comparison of back in the day, you probably would have thought IBM would be much bigger than Microsoft, but Microsoft is really, the software is something that drove computers more than the chip design did. So we are proposing a HOPE reactor. This is the homogeneous plutonium eliminating reactor. This is going to be a molten salt reactor. So with these other fuel forms like metal fuel forms, TRISO fuel forms, where you can get these really high burnup levels, you really don't have to worry about the material degradation of a molten salt. You really just have to worry about your reactor at that point. But we're hoping to put TRUfuel into HOPE itself and to bring up some really good, well, we really want some great economics for this. We want to look at beating current reactors right now and have another case for increased nuclear in the reactor side as well. So the HOPE reactor itself is a fast mixed spectrum reactor. One of the limiting factors with molten salt is you have this material concentration. It's like you'd have a certain percentage of your molten salt being actinides. That's where you get these great hydraulic levels. You'll get this eutectic melting temperature. You kind of get limited at that point though, right? And you're looking at a fast reactor, you want to make it small, you want to lower your CapEx, you have to increase the enrichment, but you're kind of limited with HALEU at 20%. TRUfuel is going to have fissile content-wise something closer to 45, 50%. So you can make the reactor core itself significantly smaller. So with this, the HOPE reactor, you have this small central fast core, and then you have a secondary blanket salt around it that would be filled with transmutation targets. Now, inside this blanket salt, you'll have a lot of, well, what we plan to do is have a lot of graphite to thermalize these neutrons that get into the blanket region. This will make the transmutation targets much more likely to capture a neutron at that point. So you could look at this as either something like starting up a thorium fuel cycle. You could have thorium in there capturing neutrons and producing U-233 to start a thorium fuel cycle reactor. Or you could have some of these long-lived fission products like iodine 129, something with a 15 million year half-life. You could put that, dissolve that into the salt and just wait till it transmutes. So you can do all of this while burning waste and hopefully making a lot of money doing it too. We have some of the neutronics here. In the solid line, that is what the flux spectrum looks like for the entire reactor. In the dashed line, the thick dashed line, that's just the core region. So you can see that looks like a fast neutron spectrum. But this dotted line, that is the secondary fuel salt. That is much closer, not quite, but much closer to a thermal neutron spectrum. So we can show here that we are getting these two different spectrum for these two different salts. So now we can use this hard neutron spectrum to really eat up all these leftover actinides and this more thermalized neutron spectrum to do transmutation with. One of the things we want to look at doing as well is making sure that the core region of the reactor that's primarily driving the chain reaction, we want that to be somewhat dependent on thermalized neutrons bouncing back in. And when you have that, you can now use reflector control. You can just drop in absorbers and cut off these thermal neutrons and just wind down your reaction in a more typical way. With these fast molten salt reactors right now, they have these very large centralized regions that are unobstructed by anything. That's how they can get these fast spectra, but it makes it much harder to control. You have to come up with different control methods. Well, right now, you can, with the HOPE reactor, you could use more traditional control methods to control your reactor. So at the end of the day, the only real waste is the way we handle spent nuclear fuel. There's a lot of value in it. And with all these isotopes, all these different fuel forms, these reactors that can come out of this, we're hoping to kind of foster a new downstream economy, not just our NuCycle facility, but many other nuclear companies, nuclear research that can be done with this type of stuff. So that is the end of my presentation. I'll take any questions if you guys have it.
Oh, thank you so much, Alex, for presenting this. My mind is kind of blown away here by like the potential of everything. For folks who have questions, please remember to put them in the chat. Had a couple of questions. Well, one was you could sort of envision using, with the move to behind the meter type reactors, or taking taking power that would go to the grid and using it for commercial uses behind the meter. You could almost envision, the closed cycle here, having a reactor right there, sort of breeding the fuel and then using that reactor to power the sort of the industrial process that does all this recycling. Is there any estimate of, like, I don't even know, like megawatts per ton recycled, any feeling of or sense of how big a reactor would take to, say, or how much energy it would take to run the plant like this?
Yeah, we're currently working with a company on kind of the full life cycle analysis of a NuCycle facility in terms of energy, carbon output, things like that. The NuCycle facility itself will need significantly less than what like a typical gigawatt reactor puts out. I can't remember the calculation exactly, but it's more of like a couple, I think it's like 100, 200 megawatts that it needs. Maybe don't quote me on that, but it's something around 100, 200 megawatts. Yeah, something like that.
Okay. The other thing I thought of, let's see. Okay, so here is a question. How does the more than 20% fissile material, oh, I lost it. Hold on a second. I lost the question. Somehow I can't see it. Whoever had that, oh, it's in the chat. Hold on a second. Here we go. How does the greater than 20% fissile material affect the licensing? The HALEU was picked, because it's licensable. Is it a loophole because the U-235 is still less than 20%? So that was the question.
Yeah, so the limit with uranium is it's more of I guess, a weapons material type thing. You can't go above 20% because then you get into HEU, and we're banned on using HEU for civilian purposes. TRUfuel itself, its fissile content is above that, but that's not U-235. The biggest fissile that's in there is plutonium-239. There's also plutonium-241. But in that case, you can't really, change the isotopics of TRUfuel. TRUfuel will also be extracted with some fission products. We're looking at exactly how much fission products to, actinide ratio that's going to be right now with a gain proposal with INL. But, this is not, weapons ready material. You'd have to take this to another facility to use that as a weapon. So this is one way of essentially getting around that.
Okay, thanks. And then and maybe Dan Goldberg can weigh in here too. I had a question that some folks may not be able to type questions in the Q&A, in which case I'd say go ahead and put them in the chat. We don't want to lose the questions, that's for sure. Let's see. The other question I had was, and perhaps I should know this, is how can you talk at all about the arrangement with how you got Curio got some or has access to some of the Byron used fuel?
Yeah, so INL has some fuel, some spent nuclear fuel that's on site. We had some of that fuel with our name on it for this project. Luckily, right at the beginning of our project, I guess by some miracle, INL got a new shipment of spent nuclear fuel. So this Byron nuclear power plant fuel was shipped to INL for research purposes. So we are they said, do you want to use some of this? It's a much fresher spent nuclear fuel. So we said, yes, of course. That's how we were able to get it.
Okay. And then again, for those who are asking questions, try again in the just at the bottom of your screen, there's a Q&A feature. Just type your questions in there. Apparently there should be, you know, fingers crossed, no issue asking questions that way. Let's see. I'm going to wait just a second to see if additional questions come in, but I don't see any right off. Oh, so one of the other questions I had was just in terms of shipping to get the reprocessing. You know, there are some states that don't allow fuel to be shipped across state lines and so forth and so on. So can you talk a little bit about, you know, any aspects of that you've thought of or have, you know, tried to get around that issue?
Yeah, that is definitely an important issue. You know, the DOE is going through this right now with interim storage, right? They're trying to take all this this diaspora of spent nuclear fuel and put it in consolidated interim storage. So they're currently working on a lot of these transport casks and stuff, but they're gonna face some resistance, and us maybe less. So right now, with a lot of these states, uh, interim storage is getting challenged a lot, right? There was a recent court case in Texas, right, where they challenged it and they won that to keep it out of the Permian Basin there. We're receiving much warmer welcomes. People seem to like recycling more than just interim storage. I guess interim storage is it's just like a big parking lot for these casks, right? But recycling, this is opening up an industrial process, and we're getting a lot of people who want these like long-term jobs that want to really reduce waste. They kind of see it as a problem and they want to overcome it. So we're getting a little bit better from that. Right now, we're spending a good bit of time engaging with states and local areas that could possibly host a recycling facility. We have been, you know, getting a lot of positive feedback. We haven't really committed to an area, and it hasn't really been an area that is, you know, publicly said they want us there. I guess some of these local places have, but we haven't really got at the state level yet. One possible way around this is to use waterways. I've heard that proposed. So it might be a good idea to have some port access for a NuCycle facility. But we'll see, you know, that's a long way down the road.
Right. Let's see if I had another one. Oh yeah, and then just, you know, there's so many participants in the group, you know, partners that you've got. You know, it seems like that the political will is strong at this point. You know, there's a lot of cooperation. Do you see, and I guess, you know, it's going to be hard for you to answer this one, is do you see like a major stumbling block, or what would kind of slow you down? You know, like what would be the thing you'd say, well, we got to go back to the drawing board? And it could be anything at top of your head. Could be the election, could be, you know, anything at all, you know.
Well, I mean, right now, nuclear is pretty bipartisan, right? It's always been traditionally liked by Republicans, and Biden's talking about tripling nuclear by 2050, right? So we're kind of in a good spot politically. Um, yeah, there's a lot of these groups going on, and there's a lot of moving wheels going on. A difficult point will probably be the NRC, right? They have not license a recycling facility. So it's going to be, fun pushing through a lot of these new things with them.
Okay. I don't see any questions, additional questions right now. So if anyone has a question, please put it either in the chat at the bottom of your screen or the Q&A. Again, we don't want to lose any questions. Let's see. And then alternately, if you do, if you have a question and you're frustrated, you can also raise your hand and I'll try to unmute you somehow.
Eric, there's a couple questions in the Q&A.
Oh, very good. Okay. Oh, yeah. So one was, have you started talking to the NRC? So that we kind of opened the door on that one. What have you gotten any feedback, or what's the preliminary feedback from them?
Yeah, we've had a couple of drop-in meetings with them. With them, you're not going to get an affirmative on this or that until you really start paying them to actually give you an affirmative. We're hoping to push that paying clock back as much as possible. I mean, you can't push that back too much, right? Because you want to actually build your project on time. But, we've informed them about our scale-up path. Right now, we are with ARPA-E doing a lab scale demonstration. We want to move after that to a pilot plant facility. This would be moving it up from the sub-kilogram scale to the several kilogram scale. And then after that, move to an engineering scale facility, and that will be pushing it up from this kilograms to up to a metric ton a year, or a metric ton a batch facility. And then we want to move to our large scale facility. So we'll have a lot of engagement with them throughout that process. And that we actually want to pursue under DOE authority.
Oh, okay. Okay. And then I have a question that kind of goes back to the beginning in a way. It says, after the decladding, fluorination, and winnowing out, what's the state of the final product that comes out of the NuCycle process?
Yeah, the last stuff that you can't get out via electrolysis will be in a salt form. And you'd have to distill your salt every once in a while to get that out. But I guess you get gas forms in the deox and the fluorination. You get a metal form if you can electrowin it out. But then you have a salt form in that final stage after, if you can't get it out via distillation.
Okay. All right, very good. I don't see any other questions, and we're close to the end here. So again, Alan, I'm going to turn it over to you. Do you have any final thoughts? Again, I have to thank you for bringing Curio to our section's attention. So just giving you a chance to add anything you want, really.
No, just really to say thanks so much to Alex and to Curio for making time for this. I hope that everybody thought it was compelling like I did. Obviously, as I always say about everything, we have a lot of work to do. But we have looks like there's a pretty good roadmap for that, and that's pretty exciting, because this is a question that comes up a lot. What do we do about the waste, right? And so for me anyway, having knowledge, a little bit more knowledge about something that's actually being worked on, and it actually has, a plan to deal with it as responsibly and effectively as has been shown here. That's a pretty big deal. So thanks, Alex.
Thanks for having me.
Yeah, and I'll add my thanks and final closeouts. I'll echo Alan. This is really interesting how you can sort of monetize or collect all the there's a saying, before you collect the garbage, you ought to know what you're going to do with it. And this really answers a lot of those questions. So as always, good luck to the team there at Curio. Again, a lot of work to do, but very, very interesting. So thanks again, Alex, to you and to Curio. And of course, we're not going away, hopefully, and hopefully Curio is not going away. So we'll have to have you back and give us an update on what's going on. With that, I'll close things out. Thanks always to Dan for setting these things up, Dan Goldberg from ANS National, for helping set these up and get these going. And thanks for those who took time out of their evening. Hopefully you found it interesting. And then for those who were there at the beginning, our ANS section is actually pretty active, and hopefully we'll become more active. And with that, we'll call it an evening, and have a good rest of your evening wherever you are.